Okay, so welcome, and today we're going to be covering networks 3-loop mesh analysis circuits. And I have a picture up here about a common mesh 3-loop circuit. Hopefully you've seen this before, and if not, hopefully you'll feel really comfortable by the end of the video. And the idea is that I'm going to go over this step by step, and hopefully after you've completed this 3 times, you should feel empowered and hopefully feel like you're on your way to mastering this stuff. All right, so here's the circuit, and the idea again is that there's a few steps, and I went over in detail in a previous video that I go over, and that video covers just mesh for 2 loops, but the technique is the same, but we're extrapolating it over for 3. Realistically, the strategy is that we're going to look at KVL, Kirchhoff's voltage law, on each loop. We're going to, of course, remember from the prior video that the system's conserved, which means that the voltages will sum up to be equals to 0. We have to definitely focus on the mesh currents. Each loop will have their own. There's always going to be a constraint, or perhaps a constraint, when it comes to 3 loops, which means that there's going to be some resistors that are affected by two different currents, or aka mesh currents. And finally, what I like to say is that I typically go with doing most of my problems clockwise. I like to say 98% because it's really not 100, but at least 98% of the time I'm going to be taking the mesh current and going around the loops in the clockwise notation. I'll explain why in a moment. And hopefully after the end of this video, you'll feel that this presentation is an eye-opener. Okay, that was funny. All right, so here's our example, so we can certainly get started with that. So this is a common problem again. You have a voltage source and several resistors, and the idea is that you have several loops. And hopefully by now it's kind of clear that there's certainly going to be 3. And if our first step is really when we identify these loops, we want to identify the mesh currents, and we're going to name it. The name is really an arbitrary name, so it doesn't matter what you call it. For the sake of this problem, I'm going to give them names I1, I2, I3. Some books use IA, IB, AC. But I like to number it because it keep it simple for me. And again, it doesn't have to stop at 3 loops, can go technically infinitely. So once you get the step 1 down, the second step, of course, again, here's my 1, 2, and 3. It doesn't really matter which one you call 1 and 2 or 3 as well. So it's really up to you as far as which one you prefer to use. So step number 2, we're going to try to write our KVL equation for each loop. And what's particularly important is paying attention to the polarities. And the one thing that we know for sure is the polarity of the voltage sources. But we also know that a resistor on its own is just a passive device, which means that it doesn't have inherently a pole or positive or negative on it. So we're going to identify that on our own. So let's try to identify everything separately. So if I were to look at this problem holistically and just look at one loop at a time, and emphasize loop 1, you'll notice that the signs and the sign convention is what we discussed in a prior video. And again, what's 100% sure is that we know that because the problem is given with a negative and a positive sign here, the voltage source has that polarity. And what we talked about the previous video is that once you leave the voltage source and you enter into any resistor, the arrow or the current entering into that resistor is going to lead to a positive going into that terminal. So in other words, you have a positive 5, a positive 26, and you go back towards the ground or the negative side of the 80-volt source. That's number 1. So now if we look at that and we try to look at it in a little more detail, I like to add letters to it, A, B, C, D, so it gives me an idea of points of reference on each corner. Makes it a little bit easier to think about this thing in this way. So I like to start generally on a corner. So if I start at position A and I go around A, B, C, D, I'm going to try to start from A and write my KVL expression all the way through. In other words, that my system should sum up to be equals to 0, hence the conservation of what Kirchhoff is trying to express with this law. So remember now that because we're reading the sign with mesh current entering a component, we can think about each component in this fashion. Again, we're 100% sure that 80 volts were given that has a minus and a positive here. But you'll notice that the 5 ohms will have positive and negative, and the 26 will also have positive, negative as well. So again, this only works because we're taking this and we're going clockwise. We're going to clockwise notation for all of the mesh currents. That's my approach, and it makes it so much easier because you have to overthink anything. So what that means is that if we were to start at position A, right, and we're going clockwise around this loop, how do we identify it is that first component is being read as minus 80 volts. And the reason, again, is because the first pole that we see here is a minus sign. What I expressed in a prior video as well is that the arrow, or with the current leading this direction, because a resistor is a passive device, it will take the sign of positive going into that component. So again, as the current goes around, right, it takes that sign of positive is what it sees first. And same strategy with the 26 ohms, right? It's going around, so the first thing it sees when it identifies it is it sees that 26. But there's an issue here, and that's what I'm trying to illustrate by this sign here. So hopefully we all agree with component 1. It's 100% sure. We should be confident, again, because the poles are given to us. Component 2, it certainly is a 5 ohm resistor, but if you recall from the actual picture, which I should probably cut and paste it for you, let me just do that to make our lives a little more convenient. I'm just going to move this image down for you so you can see it all together. So here's our problem set as a whole, and I'm going to put it here so you can see it with what I'm trying to do. And when we put this image here, right, if you look at it carefully, the 5 ohm resistor over here, although we are in loop 1, there's also a current that's in a mesh current in loop 3. So what ends up happening is that because I identified going clockwise for all of my loops, there's going to be the current in I1 that's going clockwise, and there's going to be a current across the 5 ohm. We'll also see another current that's going in this direction, right? Also clockwise, but the idea is that it's opposing the motion of I1. It's really important. So let me put a couple of pointers here so we can kind of see it more clearly. So in other words, there's also going to be a positive sign here and the negative sign on the other side of the 5 ohm resistor. That sounds wild and confusing, but it'll make sense in a moment. And certainly over here as well. So as let me put this a little more properly for you. So it's going to be a positive sign here, negative sign here, and technically it's a positive sign here and a negative sign here. Okay, and I'll express that to you. And again, I went into great detail in the previous video, but I'll say it again. So, and this one as well. But here is what's critical that I want you to walk away with this. The first thing that's critical is that, if I can find my highlighter button, is that this identification for component 2 is not correct. What's important to take away from this is that component 2 has 2 different current sources that are technically going across the 5, contributing across the 5 ohm resistor. And same with component 3. This variation is that it's not just one current that's affecting component 3, it's actually I1 and I2. Okay, so again, why is that? So let's look at it very slowly and hopefully get the hang of it. Is that as I go around from A and I1, this is all here has the same current I1 on branch AB. AD also has the same current I1, but once we get across branch BC, its I1 is definitely going clockwise here, but there's also an opposing current that's going the opposite way from I3. So let me just draw this out for you so you can see how I3 looks like. But I3 is going to look like this. It looks like it's going opposed or opposite of I1. And what we try to do, at least we can think about it this way, is we can look at it as this scenario right here. And same with component 3. It is shared among both I1, and it's also shared, okay? It's also shared over here because it's going against I1. So it's I1 versus I2. So they're kind of like going against each other. It's really interesting. Okay, so again, the 26 ohm resistor shares a mesh current. And again, the 5 ohms has the same. So let's look at that a little more detail here. Okay, so now that I drew this, and here I blew it up for you so you can see a little more clearly. So I highlighted in yellow in yellow, I highlighted branch BC, and it's showing you that the 5 ohm resistor has a contribution from the I1 current and also a contribution from the I3 current. Okay, so here's a visual of how that actually looks like, right? But at this node here plays a really important factor on this particular problem, or all problems actually. So that node is a huge deal. And again, right now it's the beginning of our circuits class. It's not such an important thing, but trust me, when you get to AC or something deeper, or Thevenin's or Norton's theorem, something else, you say, wait a minute, I think I need that. And so this is what we're going to do. We're going to try to break this down of why this is so important in hopefully a few seconds. So here's our goal. So how do we know the direction? So I'm going to give it a name. We already called the first loop I1. We call the top loop I3. But the current across the 5 ohm, we can give it a name, right? Because it's not just nothing, it's something. So what is that? And that something is that I can temporarily call whatever I want, but for logical reasons, I'll call it I5, or I could also call it IY. And remember that it's a current, right, going in the opposite direction, so I put it over here. So if we evaluate this node, right, I 100% sure know that I1 is entering this node, right? Why do I know 100%? Because I said it's going clockwise, so clockwise forces it to go up into this node. I said that I3, everything I do is clockwise, so therefore at this node, I3 is generating a loop, right, in a clockwise direction. So for sure, at this point of the circuit, I know that I3 is going to be going upwards as well. In other words, leaving this node. But how do I know the direction of I5? How do I know if it's going out or in to this resistor? And that's an important thing for us to get a feel for today. So remember, when we're evaluating the loop I1, we're looking at it for things that are entering in. From KCL's definition, Kirchhoff's current law, it says try to determine what currents are entering a node and also determine what currents are leaving a node. Okay, so that is our objective. So to summarize this and hopefully put you at ease, the first question you have to ask yourself is, what loop am I in and what am I evaluating? Because we are in loop 1. Okay, because we're evaluating loop 1, and we identified that I1 is going clockwise in this loop. That means that in loop 1, as far as the 5 ohm is concerned, I have to enter into the positive terminal. So in other words, this arrow is going to be going to the right. And I'll express that 2 more times a little bit later so you get a feel for it. So I'll say it again. So we're going clockwise here again. And because I'm evaluating loop 1, that means that the current goes around and it always enters and goes. The resistor takes on the positive sign for all clockwise notation going into the resistor. All right. If I was in loop 3, it'd be the opposite direction. Why again? Because if I'm evaluating loop 3, which we're not, we're doing KVL for loop 1 only. And because we're doing KVL for loop 1 only, we go clockwise notation and we're entering to the positive. Therefore, I5 is definitely going to go out of this particular node. All right, so what we try to do, we try to define KCL. And KCL can be defined as all the currents entering a node equals to all the currents leaving a node. So in other words, I1 is a current entering this node over here, and I3 plus IY or I5, if I change the name temporarily, will equals I1 will equals to I3 plus IY. So if I summed up KCL, said okay, sum up all if I want to prove this equation, I just essentially solve for 0 in this equation over here. So in other words, I can write it as I1 minus I3 minus IY equals to 0. Or I can call it I3 plus IY minus I1 equals to 0. And that's a classic KCL form that you see in your textbook. So why did we go through all this trouble? Because we need to solve for IY, aka I5, right? I switched the name a couple of times. So same thing. So the idea is that we found a definition for what the current of that branch is. we can call that branch I1 minus I3. Okay, so this branch over here has a definition. And that definition of the branch, again, is going to be the I1 minus I3. Okay, so it's going to become hopefully really obvious what happens now. So if we look at now the 26 ohm resistor, so which is over here, the CD portion over here. Again, notice that there's a current that's going clockwise at I1 and it's shared with I2. I2 is going opposing it. So if I highlight this picture and I show it more clearly over here, you see I1 going clockwise, you see I2 going clockwise, but it appears that I1 is going and I2 are opposing each other's direction if you were here on this branch. Very important now. This is the important part, is that as far as any time the current goes clockwise and the direction of the current is clockwise, then the resistor takes on the polarity as positive when it enters into the resistor. Same over here. So if I2 sees it this way, so as I2 comes around clockwise, it assigns a positive sign to it. There's a voltage drop associated with it on this side, and then a minus side over here, again because they're shared. So you could think of it this way: because I know with certainty that I1 is going clockwise, because I said it's going clockwise, that's my assumption with my problem, that means I could put an arrow, right? See how this loop goes, it forces an arrow. That means that I1 is entering into this node, right? Because I2 is going clockwise as well, it's going to continue along this way, so it appears as if I2 is leaving this node. So the question is, well, which way is the current going for across the 26 ohm resistor? Because we are still evaluating loop number 1, the current is going downwards. It's going from positive, right, down. All right, so okay, so let's think about that again, and it'll make sense in a moment when we get to the next loop. So again, the current across the 26 is unknown. However, it has contribution for I1, I2. We will analyze this node using KCL. Analyzing a node means that you take in all the currents entering nodes, what equals to the currents leaving a node, right? So now what we can do is that we can simplify this as we did before. You can say that I1, I called it IX this time. I keep changing my IX plus I2. We can now write it in its classic KCL form, which means I1 minus IX minus I2 equals 0. So in other words, we now need to solve for IX, and we solve for IX, we can see that IX will equals to I1 minus I2. All right, so that's how we do it. That's how we describe that current. And this is a summary image of it to hopefully help you see it a little more clearly. So now we look at loop 1, right? To summarize it again, we have the voltages. We have 3 components: a voltage component of 5 ohms and a 26 ohms, right? We know for sure that I1 is going clockwise. If I start here on the clockwise notation, I read this to be a negative 80 volts as I go around. Here is the visual of how the second component looks like. Because I'm going clockwise, I1 is going up. Because I3 is going clockwise, it's going up as far as this node is concerned. Because I'm evaluating I1 and I'm in loop I1 only, right? I'm therefore taking the stance of that the current will go enter the positive and continue on its direction, aka why I5 or IY is going towards the right. Same with this one, with this 26 ohm component. Because I'm going clockwise direction, I1 is entering that node, right? Because I'm only solving for the loop 1 equation, that means that the current will continue along its path going positive, negative. A voltage drop is what it's going to produce. So it goes positive, negative, and this arrow is going down. So I have a summary for IX and a summary for IY. Okay, so that's how you set up equation 1. So now I can write its KVL equation, Kirchhoff's voltage law, which says essentially the voltage the sum of all the voltage equals to 0. So if I go around this loop, it's simply going to now be minus 80 volts plus 5 times it by I1 minus I3, because a resistor times it by a current gives me back a voltage. And then I get to this resistor, so I have a resistor times it by a current again creates a voltage. It's going to be 26 times it by I1 minus I2 equals to 0. So hopefully you see a pattern here. So you don't actually, once you have a visual of how this works, it's essentially going to be this. If I'm in loop 1, then you leave this first current to always be where you are. So if I am in loop 1, then this is the first thing we have is I1 minus an opposing current called I3. If I'm in loop 1, I leave this here. I leave always right. If I have 100 branches that are, 100 loops that are attached to I1 somehow, they're all going to be I1 minus, the respective loop that's next to it. So in this case, it'll be 26 times by I1 minus I2 equals to 0. Okay, so that's how you do loop 1. And in loop 2, right, so it's going to practice this one more time. And if you take a look now at loop 2, you're going to see that now I'm at loop 2. I now call this ABCD. I create another box. Now I2 is my important one here. So I have 3 components. I have the 26 ohm, the 90 ohm, and the 8 ohms. Notice something special. The 8 ohm is the only one that doesn't share current of anybody else. So 8 ohms is attached only to I2. The 90 ohms is shared with the has a contribution of I3 and I2, and the 26 ohms has a contribution between I1 and I2. So let's see this again in slow motion. So here's I1. So I1, if we evaluated the node over here, right, this top node, the I1 is coming into that node. I2 is definitely leaving it. But how do we know if this arrow, IX or I26, is going up or down? Well, this time we are in loop number 2. So because we're in loop 2, right, the current goes like this. It goes clockwise. It always enters into the positive side and continues along this way. So again, it creates a voltage drop. So in other words, the arrow is going to be pointing inwards towards that node, which is really important. Because it's pointing inwards, we can now write a nice tight equation that summarizes that. So for this branch called IX, this branch has I1, this branch has I2, but this unknown branch, we temporarily called it IX. IX is going to equals to I2 minus I1, but it kind of has a pattern again. If we're validating loop 1, then it's going to be I1 minus something, but now we're in loop 2, it's always going to be I2 minus something else. Very important to keep that in mind. So for the second component, same strategy as again. So here's your node. So I1 is going clockwise again. So here's a pole. So we put the positive negatives again so you can see this. So as far as it's concerned on this node over here, this side is going to be, choose a better color, positive, negative. And on this side, it technically is positive, negative, read that way. So now when you do that, you're going to expect, because we are in loop 2, that with certainty the current's going to be going down because we're going clockwise again, down over here because I3 is going clockwise, there's entering, leaving. And how do we know the direction of IZ? Because we are in loop 2, therefore loop 2 takes precedence. We're entering that node, so that means that this value of IZ is entering this node. So if we write KCL in its modified form, which means the sums of the ins equals to the sums of the outs, we're going to get back that IZ equals to I2 minus I3. I also call these our constraints, so we have an idea of how these constraints will work out with these problems. And finally, for component 3, you're hopefully getting the hang of it by now. So when you look at component 3 of this loop, notice that the 8 ohm resistor is only influenced by I2 and I2 only. So because of that, we'll have these 3 components for the second loop. We can solve for the voltage across the 26 ohm resistor, right? It's going to be 26 will be I2 minus I1, so resistor times it by current gives me back a voltage. And this one's going to be 90 times it by I2 minus I3. And finally, because the 8 ohm doesn't share any current of any other source besides I3, it's just straight up going to be 8 times I3. And there it is, right? So notice the pattern again. It's I2 minus I1, I2 minus I3. And this one, because we already are, ooh, did I do a typo there? I did indeed. This is supposed to be, I need something that looked wrong for a moment. This is supposed to be 8 times I2, because we're in loop number 2. Okay, so with that said, I gotta fix this typo here, so sorry about that. So with that said, we can now have our equation number 2 then. It's going to be 26 times by I2 minus I1 plus 90 I2 minus I3 plus 8 I2 equals to 0. And we have our KBL done for our second problem. So we're moving along now. And then finally, for our third loop, loop number 3, our mesh loop 3, our mesh current is called I3, right? We have 3 components again. Our 3 components are the 5 ohms, the 30 ohms, and the 90 ohms. And notice that I put the sign convention on it again, so the current will always enter, if I'm going clockwise, the current will always create a voltage drop, which means it's going to be positive, negative, positive, negative, positive, negative, always if I'm going clockwise. And notice again that I3 contributes only to the 30 ohm resistors, but the 90 ohm resistor is shared with I3 and I2. And so here's I3 and I2 affect the 90. And the 5 ohm resistor over here is affected by I3 and I1. Okay, so now that you've figured out the pattern for the other 2 loops, look how easy it is now. It's going to be 30, right, which is our top resistor over here. Multiply that by I3, because there's nothing else affecting it, plus 90, which we're over here now, times it by, we're in loop 3, I3, and we're going opposed, I2, and then plus again, 5 ohms, times it, and we're in loop 3, so it's going to be I3 minus I1 equals to 0. And there you have it. We have our 3 equations for this problem, and we're actually ready to solve for the current. So this is all it takes. To summarize now, and I see my typo here, I've got to fix this. Oops. So in summary now, we're going to have 3 equations and 3 unknowns. So our objective is to simplify this problem and complete. So our goal now is to take these 3 equations and do our best to not make any algebraic mistakes, to simplify it and solve. Okay, so once we do that, we should be able to simplify it in this form. So kindly try this out. So what I tried to do here, and I noticed now that I must have went back and fixed a mistake somewhere at some point later. So when you simplify this, right, you're going to take these equations and essentially simplify it, and notice that I'm going to be left of 31 I1 minus 26 I2 minus 5 I3 equals to 80 volts. And I'm simplifying it by realistically just distributing out these problems, right? And I do the same for I3, and I simplify it as well. I combine all my like terms, my I1, I2, I3, and eventually, so I'll slow down a little bit so I can take a screen grab of that. And eventually, what ends up happening is that we have 3 equations, right, and 3 unknowns. So here it is. Here's a summary of this. We're going to be left with I1s, I2s, and I3s, right? And notice I put them all in the same pattern for a reason. Because if we try to do this problem, by the way, using substitution, it might be here for a while. And this, so now technically we're 80-90% done with the problem. The rest is just solving for these unknowns. And the strategy for me is not to do substitution because I'll be here for a while, but here at this point, I'll use a work of matrices, our Cramers rule, or a method to get this problem done. And again, Cramers rule to me is the fastest way or more efficient way once you get comfortable with it. And if you already know how to do that, you can stop and move on. But if you're not familiar, keep watching this video for a little bit. But the idea again is that you notice that you can have an A1X plus B1Y plus C1Z equals to D. And again, it has this pattern as well. You can take a look at some information about Cramer's rule, but the idea is that we're trying to solve for determinants. We're trying to create this matrix using all of our variables that are given from our particular problem, and we try to then solve for example, for this problem, X, Y, and Z in this pattern where D's, right, will be the solution to our problems, right? And we're just moving them into these 3 places. So take a look at that, and if you want, I can go ahead and pause it, and I will certainly solve the problem from here to give you so you can get a little bit more comfortable with it. So once we have that done, our objective now is to put it into this matrix form. So I'm taking this problem, I'm taking all of my unknowns, the 31 minus 26 minus 5, and I'm putting it into a matrix in a matrices, and I put it into this form. I solve for this determinant using what I showed you before, and if you've never done it before, it's hopefully not so bad. So what I like to do is, I guess this is called, I think it's called the first or second method of Cramer's rule, is I cross out the first row and column, right? And I create these simpler matrices of 124 minus 90 and minus 90 125. So I cross multiply them out, 124 times by 125 minus 90, and then I subtract minus 90 and minus 90, and I multiply it by this fact there, which is 31, right? And I get back a fairly large number, 229,400, okay? And I do that as I showed you before for solving for x and y and z, and I do it again. And I think in the previous video I actually went over this in a little more detail, but I'll make a separate video for this if you like. And the idea again is that then I'll have here the negative 26, and I'm multiplying it out. I cross out this entire row and this entire column, and I now do cross multiplication of the minus 26 times it by the 125, subtract it from the minus 5 times it by the minus 90, right? And I get a number again, and the number of minus 96,200. Then I add that to my final matrix to get to the minus 26 minus 5 and then 124 minus 90, and I did the same Cramer's rule operation again, and I have a value of negative 14,800, and that determined I get a fairly large number of 118,400. Okay, and finally I continue that to solve for my value of I1, and as I showed you with the x, y, and z with the Cramer's rule, so now I substitute in my values of d1, d2, and d3, aka the solution to my first equation, second equation, and third equation, and I do what I did before. So I do 80 times it by the 124 times the 125. I already got this answer from earlier. I get a fairly large number, and the rest is easier because 0 times it by anything gives me back zeros. So finally, with going through all these steps, I do 592,000 by 118, 400. I get back the current, for example, of loop 1 to be 5 amps, a nice clean number after doing this problem. Again, if you're unfamiliar with Cramer's rule, I can create a separate video just for Cramer's rules to get you a little more familiar with it. But it's hopefully something you're familiar with from your math classes. And I do the same, and I continue this. So I can solve for values of I2 and I3 as well. And if you work through these problems, I end up getting 2.5 to be I2. It's again solving for the system of equations. And then finally to solving for I3, right? And here's my proof here. I get back a value of 2 amps. Okay, so we're able to show, well, hopefully without too much pain and suffering, 2 amps, 2.5, and I think what I said before, and 5 amps to be our solutions to this problem. Okay, all right, so again, the heavy lifting, what you should get out of today is certainly that this is something that you can do. This is something that certainly the most important thing realistically is how to start. Getting started. Really what I feel that was the most challenging for me when I started learning this stuff was figuring out the directions of the currents. It was really confusing at first when I first learned this. So, well, okay, which way are things going? Some people don't really care, but I think it makes a huge difference if you understand it now versus later. And then after that, when you get to the more challenging problems, this will hopefully be a cakewalk. Okay, so I'm gonna make separate videos about other stuff as well. So if you like what you learned, please like or subscribe, and I'll continue making videos like this, and I'll see you guys soon. All right, it's been a pleasure.